anytime homework?
So in the homework, there were some questions from chapter 8. So is that part of what we should know?
Well, what is it?
It was about solids, like crystalline solids.
Yeah, we're gonna do solids.
Okay.
Yep.
Okay.
We might not get to it tonight, but we'll get to it on Thursday if we don't tonight.
But it's just confusing because it was a jump ahead in the book, but I was like, okay.
Yeah. Anything else? 'Cause
Ionic compounds are a non-metal and a metal. Right?
that's right. For the most part.
Covalent is both, not like two non-metals.
Uh-huh. Yep. Any other questions? All right. So let me start with, on Tuesday was our scheduled exam. I was going to do it in class. Something come up and I'm not going to be able to be here. So I gave you till for Monday, Tuesday, or Wednesday to take the exam in the testing center. So if you schedule it right now, then you might be able to schedule it for this time. I don't know what time they're open, but does anybody know their
I
hours?
think they're open till 8.
Okay, so you should be able to schedule for this time if that's the only time that works for you. But I gave you Monday, Tuesday, or Wednesday to do it. Okay? That gonna not work for anybody?
I
Okay.
don't even remember how to schedule at the test center.
You go to your MySLCC and then you sign in and you find the testing. And maybe there's another way to do it. This is the way I do it. And then you just click on, I don't know.
I'll figure it out.
It probably looks a little bit different on the student end than In my
That's
end.
free. If you look it up, it'll.
okay. We good? So I will send out a email to everybody, just reminding you what you have to do. And they will give you a periodic table and a reference sheet. You need a calculator, something to write with probably. I think they give you a whiteboard, erase marker and stuff like that, but if you want paper, you can request paper and just bring a pencil or something. And they will shred your paper when you're done, but yeah. Any questions? All right. Today we're talking about polarity. So polar molecules are a covalent. So let me change it. I'm not going to do polar molecules. My bad. We're going to start simpler. A polar bond is a covalent bond where electrons are not shared equally. So what would make so that they're not shared equally? Any ideas? Atoms have different electronegativity values. Remember electronegativity? That ability to take in electrons more than the other one. Okay? So to determine if the bond is polar, follow a few steps. Step 1, determine the electronegativity values. And we got a whole chart that you get for the exam, so you don't have to memorize this. Then step 2 is we determine the difference in electronegativity. That's the important part. So the difference in electronegativity, or we can say a change in electronegativity, is equal to electronegativity value 1 minus electronegativity value 2, but it's always going to be positive. And how do we write always positive in math? Absolute value. If that one makes you want to throw up, then just write this. Good? So basically big number minus small number. That's it. And step 3 is we specify which atom is partially positive and which atom is partially negative. And the symbol we use for partial positive is the Greek letter delta with a plus sign. Or partially negative. And that's a Greek letter delta with a negative. So how do you tell which one's partial positive, partial negative? If one's taking electrons more, it's going to be more what? Positive or negative? Electrons have a charge of minus or plus? Minus. So if it's bringing in more negatives, it's more negative, right? So whatever one has a highest electronegativity value is more partial negative. Good? Whatever one's lower is partial positive. Okay, that's a bunch of words. Maybe it doesn't mean a whole lot until we do an example, right? But before we do an example, I want to give you a little scale to follow. So this is 0, 0.5, and if we have a difference in electronegativity has a value of between 0 and 0.5, then it's nonpolar. Yep. Good. And you guys know this notation where we have a bracket versus a...
Inclusive, exclusive.
Yeah. So if it's bracket, it includes that. If it's a parenthesis, it doesn't include that. So this is basically saying if the difference in electronegativity is less than, not equal to, but less than 0.5, then it's nonpolar. And it's never going to be negative, so, okay. And if it's greater than or equal to 0.5, then we call it polar. And that's just for a single bond. Well, or a double bond or a triple bond, just a bond, right? Yes. Okay, this is just for our first step of a few here. So let's practice this, make sense of what we're doing here. So example 1, if we have a carbon-hydrogen bond, first step is determine the electronegativity values. So do you guys all have this electronegativity chart? I gave one to you a while back. I will give you one on the exam, so you don't have to take one to the exam or the testing center. What's the electronegativity value for carbon? 2.5, and what is it for hydrogen? 2.1. So if we want to find the difference in electronegativity, it's going to be 2.5 minus 2.1, which is equal to 0.4. Is that polar or non-polar?
Non-polar.
Do I need to unlock that door? Unlock that real quick so that in case that happens again. Was that locked? So is this a polar or non-polar bond? Non-polar. Good enough? If it's non-polar, then we can skip the next step. We don't have to worry about partial positive, partial negative, because it's non-polar. So, see how there is a difference? Slight difference, we could just say that's negligible, okay? So basically, they kind of share equally. Good? Okay, example 2. Let's do a carbon-fluorine bond. Carbon is still 2.5, fluorine is 4.0.
It's the most.
Are we good?
It's the most.
Yeah, the fluorine is the highest electronegative element on the periodic table. And so the difference in electronegativity is 4 minus 2.5, that's equal to 1.5. So what is it, polar or non-polar? This is polar, therefore we have to determine which side is partial positive, partial negative. Are you with me? Which one's partial negative? Fluorine, because it has a higher electronegativity value. Good?
It's partial negative,
Yes.
higher negativity.
Higher electronegativity means it's more negative, partial negative. Good? So that's a partial negative here, partial positive there. That looks like an 8. Let me start that again. Partial negative, partial positive. And if you guys don't want to draw the delta, it's not the end of the world, I promise. Okay? But that's the symbol we use. Okay. We following so far? Any questions? Okay, example 3. Oxygen-nitrogen bond. Oxygen's electronegativity value is 3.5. Nitrogen's is 3.0. So the difference in electronegativity is 3.5 minus 3.0, which is polar or non-polar?
Polar.
Barely polar. So if you look at this scale, if it's 0.5 or greater, right? Greater than or equal to 0.5, we're gonna call it polar. Now guys, gals, this is not in stone, it's not. You look on the internet and it'll say 0.4 or 0.5 or something, okay? This is just a kind of a general scale, and we're gonna stick with it, okay? And we're gonna just keep it simple, okay? How are we feeling? Need another example, or can you do this? Another one? Okay. So on your worksheet that you picked up today, let's do section 2. Let's do,
Can you say again, how do we know, like, for example, the
electronegativity.
Yeah, or oxygen, for example.
So we're gonna look at our periodic table that you get on the test, and it has this chart at the bottom.
Oh, yeah.
And this chart for oxygen says 3.5.
Oh,
So you do not have to memorize those.
that's great.
You get this on the test, use this. Good? Yes. All right. So let's go to section 2 on our worksheet. Section 1 just says, what's the electronegativity value? You just look that up, guys. If you want to practice that on your own, you can. Do you have to memorize these? No, you don't. So let's do one from section 2. Let's do Cl and a nitrogen bond. What's the electronegativity value for nitrogen? 3. What is it for chlorine? So is this polar or non-polar? Because the difference is 0. That one's absolutely non-polar. Good? Well, that one was an easy one. They're all easy. You get this? Do you want to go over another? Is there one that you want to go over?
So, where's 3.0 coming from again?
That's coming from this electronegativity chart. You just look it up. And it is on Canvas if you need one. You can take a picture of this one. I don't have an extra copy, but you can take a picture of mine here if you wanted.
And so if it's over 2, I think they said that means it's ionic.
Yes, but does that mean you can't have a polar covalent compound that's over 2?
So these are
So
generalized
it's
rules.
yes, it's a general. That's why I didn't even write it, because yeah,
These are kind of.
because there's an easier way to tell if we have an ionic compound, if it has a metal in it, right? Or if it's made of ions. That's the easier way in my mind. But yeah.
Interesting.
So if it's 0.4, it's non-polar,
Non-polar.
and 0.5,
It's polar.
polar.
Yep.
Like, how do you say? Forward?
Yep. 0.5 or bigger.
They're bigger.
Yep.
Okay.
Yes. Are we good?
Yes.
All right, let's move on now to determine, so that was just a partial step to where we're going. Let's determine if the whole molecule, the whole compound is polar or not, because that's really what we're interested in. How to determine if molecule is polar or not. Step 1, Determine/draw molecular geometry. Do you remember this? We learned that last time, so we can use it this time and for the rest of this course. Maybe not every little detail in this course, but we'll use it. Okay, and I want to give you a note here. We don't want to just draw the Lewis structure. Do we have to draw the Lewis structure to determine the molecular geometry? Yes, but we have to know the molecular geometry to move on. Okay? Not Lewis structure. And this is where a lot of people make a lot of mistakes. They just draw the Lewis structure and move on. Yeah.
Is that why you were talking about getting the models?
Uh-huh.
Is because of this?
Yep. And you can use those models on the exam. Okay. Step 2, determine if each bond is polar or not. That's what we just barely learned. And not just one bond, but each bond in the molecule. And something to kind of make note of. If central atom has any lone pair of electrons, we can say that it's a polar molecule. That's a good thing to know. There are a few exceptions, though. And do you remember the diatomic molecules? H2, N2, O2, F2, Cl2, Br2, I2, all of those, there's 7 of them. Those ones will always be nonpolar, even though some of them have lone pairs. But if you look at the difference in electronegativity between 2 of the same elements, what is it? 0, right? Other than those, if your central atom has a lone pair, it is a polar molecule. If you don't want to remember this, you want to just go through all the steps, you can. Okay? Step 3, perform the line test, or the straight line test. Well, a line is straight, so I don't have to write that, but I will. Okay, and here's how you read the straight line test. If you can separate the partial positives from the partial negatives, then it is a polar molecule. If you cannot separate them with the line, it's nonpolar.
What does that mean?
The line
Separate
test?
them with the line?
Okay. Yeah, let me show you a couple of polar objects that we're familiar with. Something that has polar opposite ends, like Anybody know what this is? Now do we know what it is? Well, a magnet, right? Magnets are polar opposites. Magnets are polar objects. We can draw a line that separates the poles. Good? Now that has nothing to do with positive and negative. Is there an object that has positives on one side and negatives on the other side? Whoa, let me try that again. What is that? Oh, I knew I should have went into art. Just we can draw a line that separates the positives from the negatives. Batteries are polar opposite ends, right? Batteries are polar objects. Magnets are polar objects.
What's something we can't draw?
Our bodies. Well, that's wrong. Well, we'll show you some molecules that you can't draw the line.
So for step two there, is that because it makes a asymmetrical molecule?
Yep.
Ah.
Yep. And I've taught this for a lot of years, and I come across this little cool, these steps here, like, oh my gosh, that would have helped my students a lot more. Because we can talk about physics and vectors. You guys want to do that?
No thanks.
I don't need anything more in my
Okay.
brain. I don't.
We could. This takes the physics out of it. I mean, it's still physics that tells us what it is, but this is an easy way to determine. Okay? You ready for some examples? All right, here we go. Let's do carbon dioxide. Are we okay with drawing the Lewis structures, or do I need to go through step by step on here? So I can just draw it for you? Okay, the Lewis structure for carbon dioxide looks like this. So what is the molecular geometry? Because that's the very first step here. What is the molecular geometry for carbon dioxide? How do you know it's linear, Maya?
Because it's straight.
Yeah, because, well, hold on a sec. Can we just go by the shape by just the Lewis structure? We cannot. You're right on this one, but, for example, if I drew water like this, is that linear? No, it is not. Okay? So you can't, and this is what I was saying before, you cannot just go by the Lewis structure. Okay? So how do you do the molecular geometry? You count the electron regions. 1, 2 around the central molecule. If there's only 2 regions, what is it? It's linear, right? Okay. Now we got to determine each bond, if each bond is polar or not. You determine the electronegativity value. Oxygen is 3.5, carbon is 2.5. Weird. So is the carbon-oxygen bond polar or non-polar? Polar, because the difference is 1. 3.5 minus 2.5 is 1. You with me? Okay. So it's a polar bond, meaning which side is partial negative, the oxygen or the carbon?
Oxygen.
Oxygen is partial negative. That makes carbon partial positive. And this is the molecular geometry. It's linear. Can we draw a line that separates the positives from the negatives? Anybody want to try? If I draw it right there, do I have positives on one side and negatives on the other side? No. Well, that wasn't a straight line, Mr. O'Brien. Ah, sorry. I always use that one for my high school students. I'm sorry.
Say that again.
I called myself Mr. O'Brien. You guys don't have to call me Mr. O'Brien, okay? All right. So, what if we draw it here? Positives one side, negatives on the other?
No.
Any way we can draw this? No. So this is non-polar. We can't make it look like a battery or a magnet, guys. So it's non-polar. Good? Anybody want the vectors? The physics? Okay. You don't have to take it. You could just not listen for a minute, but I did see it say I want to know. Okay, here's a dipole. The positives on this side, and it's being pulled toward more negative, right? You got one right there, and you got one right there. They're the same strength. So if I have somebody pulling on this table this way, someone pulling on this table this way with the same amount of force, what's going to happen with this table? Oh, it might break if it's enough force, but probably just nothing, right? Okay, probably just nothing. So nothing's going to change. No change, non-polar. If we have a net force, a net dipole, then it's polar. But guys, the line test will just take care of all of that. Okay? Let's do another example. Any questions on that one?
If we weren't doing so if you can separate it, it's non-polar or polar?
If you can, it is polar.
Okay.
Why? Because you can with a battery.
So then if we weren't using the line test and we were using the electronegativity, how do you?
Then, well, we do use the electronegativity. We have to.
For
So
bonds.
we check each bond, and then if the bond is polar, then we determine which side is partial positive, partial negatives. Then once we have everything partial positive, partial negatives, if we can separate the partial positives from the partial negatives, then it's polar. If we can't, it's non-polar. Do you get that?
So for a really complicated molecule, would you have to do all those vectors
You-
to get that net force? Basically, that would be easier,
It's easier just to do the line test.
even in.
But yes, you could, and I can show you if you're interested. I probably won't draw it all out because it's hard to draw 3D on a 2D plane.
Mhm.
But here we go. So let's do NH3. So we drew this one last time, something kind of like this, right? Is it polar or non-polar? If we have any lone pairs around the central atom, it is polar. Now let's pretend we don't. I just want to go through these steps. Here we go. What is the molecular geometry for this? We have 4 regions. 1, 2, 3, 4, right? 1 lone pair, so it's going to look something like this. You with me? Now you look at each bond. Hydrogen is 2.1, nitrogen is 3.0, so that's a polar bond. Partial positive, partial negative. You with me? Can we draw a line that separates the positives from the negatives? Yes, that is a polar molecule. Good?
And is it true, I can't remember if I heard this right, but the first element in the formula is usually
The central atom.
Well, it goes from, more electronegative to less electronegative in the formula?
Like No, usually the central atom is least electronegative, but hydrogen can never be that, and that's why it's different here.
And I said it wrong. That's why I was thinking like more negative, less negative, yeah,
Yeah,
because it's an absolute value.
uh-huh. We good? Some more?
Small?
Yes, please, give me some more, this is so fun. Okay, or give me some more, because we don't get it yet. What is it? Okay, so we got C2H6. Oh, we got 2 carbons, 2 central atoms. Well, let's do this. If we draw this, in fact, should I show you how to draw this one, because it's icky?
Yeah.
Okay, 2 carbons, 4 piece, right? This is 1 times 6, are you with me, on counting valence electrons? So that's 8 plus 6, that's a total of 14 electrons. Which one's the central atom?
Doesn't matter.
Carbon is.
Or-
But it
or
doesn't matter
carbon.
which carbon, yeah, both of them, they're bonded together. And then we got 1, 2, 3, 4, 5, 6 hydrogens. Now, is that the molecular geometry? It's not. Here's what it looks like. Oops. Something kind of like that, right? Don't worry about drawing this, guys. You don't have to. So if we say this is the central atom, right, there's 4. But now we got to look at the carbon-hydrogen bond. Is that a polar bond or a non-polar bond? 2.1 and 2.5. Non-polar. Non-polar, 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 non-polar. What about the carbon-carbon bond? Difference in electronegativity is 0. Non-polar. We have 0 polar bonds, so what do you think? Non-polar. Okay, the converse is not true. If we have only polar bonds, doesn't make it polar. You gotta do the line test. But if we have 0 polar bonds, it's non-polar. Because why? We don't have to draw any partial positives, partial negatives, so there's nothing to separate. Good? Questions on that? Okay, what about CCl4? If we draw the structure, something like this. We got to know what the shape looks like. Tetrahedral, because there's 4 regions, 0 lone pairs. You with me? Is the carbon-chlorine bond polar? Chlorine is 3.0, carbon's 2.5. It is polar, right? So that means this is the partial negative, partial negative, partial negative, and this is the partial positive. Can we separate those? We cannot. This is 100% symmetrical. When a molecule is 100% symmetrical, it is nonpolar. You can remember that, or you can just try doing the line test. You might want to just try doing the line test, right? The line test, we can't draw a line that separates. There's negatives everywhere. We can't draw a line that separates the positives and negatives, so this is nonpolar. Even though all of the bonds were polar. Okay? Yeah.
Are they going to give us the structure, not the Lewis one, but this?
They will if it's big like this.
Okay. But other
But-
than
but-
that, we
but
have to
for the ones-
memorize the other ones.
Yep,
Oh,
yep.
great. That's fine, cause I would not have known that one, so.
Yeah, you don't have to do, so this is organic. We're not gonna do organic structures. There might be one on there. For example, it might say, okay, we have this, and it might draw it as a 3D structure, but we have something like this. Whoops, let's do that. We can call this carbon 1 and this carbon 2. And it'll give you like this on the test. It says, what is the molecular geometry for carbon 2? And you would say, oh, there's 1, 2, 3 regions, 0 lone pairs. What is it? What I'm talking about, what is the molecular geometry?
Oh.
Trigonal planar, right? It might ask you a question like that on the test. And for carbon 1, what is it? One, two, three, 4 regions. 0 lone pair, that's tetrahedral. Good? I'm not going to worry about polar or non-polar right here. Good? Let's do one more. H2O. If we draw it, our Lewis structure looks something like this. Do you have to draw it like that? You don't. But that's the most common way people draw it. Is that what the geometry looks like? No, you have to draw the molecular geometry. We have 1, 2, 3, 4 regions. So this is going to be tetrahedral shape, right? 2 hydrogens there. 2 lone pairs here. Something like this, yeah? And then we check the bonds. Is the oxygen-hydrogen bond polar? Yes or no? This is 2.1. This is 3.0. Difference is 0.9. Is that polar or not? It is polar. Which side is partial negative? The oxygen is partial negative, more electronegative. That makes the hydrogen partial positive. We draw a line that separates the positives from the negatives? Yes, because it is bent. If we say it's linear, we'd say no, but it's not. That's why we have to know the molecular geometry. Questions? Too much? This is heavy stuff, guys.
So even with, so another way we can tell it's polar is if it has those lone pairs, right?
Yes. That's the easy way. We see that there's lone pairs around that central atom. It's polar. We can stop. Good. We're good? That lone pair makes it so it's not symmetrical. When it's not symmetrical, it's polar. When it is symmetrical 100%, it's nonpolar. Okay, do you want to try some more on your own? Or do you want to try some more together? What do you want? You have a worksheet. Tell me what you want. Okay. So I will post the answers in just a second. Go ahead and try. I would do section 2 on this worksheet. Section 1, let's see, no. Is it section 2? Section 3 and section 4. on that table back there? Is there any more?
No, they're out.
Really?
Mm-hmm.
Huh.
You gotta make more.
I can take a picture of mine.
Yeah, I already took a picture of mine too.
Oh,
Or you can take your picture of this one.
I'll just take a picture of this one. I'll bring it back.
I don't need it.
Oh, okay. I'll keep it then. Thank you.
Thank you. Huh, okay. Yeah, I'll start printing more. This one right here looks like it goes against what I said. If it has lone pairs, it's polar. In reality, this is a polar molecule, but it's not very polar. But for this class, we're not going to have to worry about that. Okay? Because of its we call it asymmetry, then it makes it polar. But we're going to keep it simple in this class. So why is that one on there? I have no idea. I didn't make this. But these answers are also on Canvas.
Okay, so we won't have to specify slightly polar.
Because if you look at that one, the selenium and hydrogen bond is nonpolar. So according to the rules I gave you, you have 0 polar bonds, so it's not polar. But in reality, it's slightly polar. So these ones are drawn to show you the vectors, but you can use the line test. Yeah, they're all gone, so if you want to take a picture of this, you can. Or if you have a device, it's on Canvas.
It's on Canvas, you said?
Yeah. If you can't find it, let me know. How we feeling? More time? Any questions on these, any of these? We can do some more on the board if you'd like, whatever. Or if you want more time, just say, shut up.
Quiet.
Okay.
Do you have a video of all of this in the platform? There is video,
I have one from last semester, yeah.
and it's the same explanation.
And I will put this one on by probably tomorrow.
Because I have to leave early,
Okay.
and I don't understand.
Yeah.
But I can, if you can see the videos.
Yeah, this is tough, huh? Okay, good luck.
And the test is like next Tuesday.
A week from today. Well, Monday, Tuesday, or Wednesday, in the testing center.
Do we need to make an appointment?
Yes.
Or to schedule it?
So make the appointment for your test as soon as you can, especially if Tuesday is the only day you can do it, right? Tuesday night. So, but you do have Monday, Tuesday, or Wednesday to take it.
So we don't need to come to here.
Yeah, we will not have class next Tuesday.
It's gonna be in the testing center. We have Monday, Tuesday, or Wednesday
Yep.
to make an appointment. We
So I would make the
online.
appointment this week,
Yeah.
and then, yes. So go to my SLCC.
Whichever testing.
Yep.
center.
Anyone you want.
Anyone. So we don't need to bring our laptop.
Nope.
So we only bring the,
No, they will have a reference sheet and a periodic table.
okay.
They'll
So
give
we
that,
just bring the calculator
bring a calculator, something to write with.
and
Something to write with.
something to write with, okay.
They'll give you paper or a whiteboard and dry erase marker. So, whatever you prefer.
And we can bring note like they have them for, they give it, they'll give us. Okay.
Yep. And I'll send out an email to tell you all the details.
And it's gonna be questions like, multiple choice.
Yep.
Everything's multiple choice. Like the other one. But no problem. Pretty much like the study guide.
Yep, look at the study guide. So, ladies and gents, review that study guide before next time. Because whatever we don't finish today, we'll finish next time, and then we'll have extra time. We can go over review. Yeah. There is.
Wait, what's?
And so ladies and gents, the practice tests are worth what, 20% of your grade?
Yeah.
Do them. Do them. And it's to your advantage anyway.
It's only 2 attempts to do it.
You have 2 attempts, and there's also videos on Canvas that tell you how to do it. So for your second attempt, not just to get full credit, but make sure we understand what we're doing, yeah.
Said study guide.
I gave you a study guide at the first of this unit. If you want to take a picture.
That's on camera.
I do have, not this one.
Oh,
I do have some study guides if anybody needs them.
Yeah, I'll take one.
Okay, do we have any questions before we move on?
Yes.
Yeah, what's up?
Okay, let me just pick a random one from that. CH2O.
CH2O?
So, yeah.
All right. So let's draw the Lewis structure. So we got 4 for carbon, 1 times 2 for hydrogen, and 6 for oxygen. You with me? So we got 12 electrons. Carbon is the central atom. Something like that, right?
Yes.
So far we used 2, 4, 6, so we have 6 electrons left. We put them around the oxygen first, 2, 4, 6. Now we don't have any. Does everybody have an octet?
No.
Carbon does not, so what do?
Share one.
Make a double bond. Okay, that's the Lewis structure. Now we got to do what to determine if it's polar? Molecular geometry.
this for the separate. VSEPR.
Yeah. Okay. So we have how many electron regions?
But it has lone pairs, so wouldn't we know it's just polar?
No.
No?
This is not the central atom.
Oh, only on the central atom.
Only on the central.
Okay.
So we have I'm glad that came up. 1, 2, 3 regions. 0 lone pair. So what's the geometry?
Trigonal planar.
Trigonal planar. Looks something like this. Is it 100% symmetrical? No. That in itself, we could just say it's what? Polar. But let's keep going. Is this bond polar, and this bond polar? We got 3 bonds to check. Carbon-hydrogen bond, is it polar? Non-polar. Now, ladies and gents, this is a good thing to remember. If a compound has only carbon-hydrogen or carbon-carbon bonds, it is always non-polar. So if you have a compound that only has carbon and hydrogen in it, it is non-polar. So if we have C8H18, oh, I don't want to draw that. We don't have to. Right? Because it's only carbon and hydrogen. That's gasoline, by the way. And so this is non-polar. Non-polar. Is the carbon-oxygen bond polar? It is polar. So which side is partial negative? Oxygen or carbon? How do you tell? Whatever one is, the more electronegative is partial negative. Can we draw a line that separates the positives from the negatives? Easy. I mean, yes, we can. Are we good?
Have no non-polar hydrogen.
Oh, the carbon and hydrogen?
Yeah.
Good. So hydrogen is 2.1, carbon is 2.5. What's the difference? 0.4, and that is nonpolar. Good? So nonpolar, nonpolar, then we just have to worry about the carbon-oxygen. Because if it's nonpolar, we don't draw partial positive, partial negatives. Any other questions on that one? Anything else before we move on? All right. The next part we're going to talk about is intermolecular forces. And we abbreviate it IMF because it's such a long word. Now let's make sure we understand what intermolecular forces are. So a force is a push or a pull, right? In the case of talking about molecules, it's an attractive force or a repulsion force. And basically they are attractive forces. But if we have a water molecule, which is bent, we're going to have, if we have one molecule of water, we have trillions of them, right? So I'm going to draw another one right here. Is water polar or nonpolar? It's polar, okay? That means the oxygen is partial negative and the hydrogen is partial positive. What happens to positives and negatives? They attract. So we don't have a bond here, but we have an attraction. This attraction is called the intermolecular force. Does that make sense to everybody what an intermolecular force is? So an intermolecular force is not a bond. It's just an electrostatic attraction. Okay?
Like two magnets in between. Yeah.
So two magnets are kind of, yeah. Or even better, a balloon rubbing on your head. It either attracts or repels, right? Yeah. Uh-oh.
I have a longer one if you want it.
That's okay. Thanks, sir. I appreciate it. I'll just do it in my lap. Thank you, though. All right, so there are 4 different types of intermolecular forces. And I'm just going to draw a table. So I'm going to do type. In fact, before I do this, I'm going to leave some space on the left side and the right side. So in your notes, so type and type of compound. So type of intermolecular force and then type of compound. So the first type is ion-ion. If we're dealing with ion-ion intermolecular forces, what kind of compound do you think we're dealing with? Yeah, metals and nonmetals. What kind of compound is that? Ionic. Yeah, are we good? Yeah. So this is between, between ionic compounds. Good? So if we have a metal in it, metal and a nonmetal, we already know what it is. We don't have to worry about polarity or nothing. Okay? Next is hydrogen bonding. We call it hydrogen bonding, but we're not talking about bonding to hydrogen. We're not. Okay, we'll talk about it in a minute. This is between polar molecules, polar covalent compounds. You guys know what a molecule is? molecule is the smallest particle of a covalent compound. So basically, it's a covalent compound, okay? So between polar molecules, but specifically, when hydrogen is directly bonded to nitrogen, oxygen, or fluorine. Why those three? Any ideas? Those are the three highest electronegative elements on the periodic table. Next one, am I going too fast? It's dipole-dipole. These are also between polar molecules. So these are the ones that are not between hydrogen, oxygen, hydrogen, fluorine, hydrogen, nitrogen. The rest of them. And the last one is London dispersion. Any guesses what these are between?
Non-polar.
Non-polar. Okay, on the left side of this, as we go up, the strength of the intermolecular force increases. And on the left side, it's the same arrow as it goes up. The boiling / melting point increases. So now we're getting into the properties that are determined by polarity. So why does the boiling point increase as the intermolecular force increases? Let's think about this. So as we have liquid substance, to boil it, we give it heat, right? Well, this liquid substance, they're kind of close together, right? They're kind of close together, and if we heat it up, what happens? It breaks the intermolecular force, so it makes them go farther apart. And now they're gas. You with me? So for ionic compounds, it takes a lot of heat to get those things to come apart, because their intermolecular force is so strong. As we go down, intermolecular force is not strong at all. In fact, like methane, which is nonpolar, it's already boiled, right? Same thing with melting. If it's a solid, they're even closer together. You melt it, kind of breaks them apart a little bit. That makes sense in everybody's mind?
Yeah, that diagram where it showed like the drop off in the boiling or the melting point between hydrogen and carbon, kind of that solidified it for me.
Good. All right, so let's practice determining what type of intermolecular force we're dealing with. Unless anybody needs this still. We good? All right. So let's do H2O. So first of all, should we write some steps on doing this? Steps for IMF. First of all, we got to determine what type of compound it is. If it's ionic, what kind of intermolecular force is it? Ion-ion. If it's covalent, then it's one of these three. Good? So if it's covalent, now we got to check what? If it's a polar molecule or not. And if it's polar, then it's one of these two. Or if it's nonpolar, we know it's London dispersion. So if it's polar, then we move on and we determine if hydrogen is bonded to nitrogen, oxygen, or fluorine. That's it. If it is, it's hydrogen bonding. If it's not, it's dipole-dipole. Okay? Okay, as much as we can be? Okay. This is a lot, I know. And we'll stop when we stopped in the last class, unless you guys want more. You let me know. We're almost there. But if we stop, that doesn't mean you should stop. It means you should study within the 24 hours, right? Get this down. Otherwise, it'll slip your mind and say, ugh, this is hard. Okay? So let's do one. Let's do water. Is that an ionic or covalent compound? Covalent, there's no metal in it. So we have to check to see if it's polar. So to do that, we draw the Lewis structure first of all. In fact, we did this one already. Does anybody remember what it is? Oh, this is a polar molecule because it has lone pairs. But if we didn't catch it, we can draw it out. There's the molecular geometry. Partial negative, partial positive. We can draw a line, so that's polar. Okay, so it's polar, so does that mean it's hydrogen bonding or dipole-dipole? Why? Because hydrogen is bonded directly to oxygen. Hydrogen bonding. We good? Okay, let's do another one. N2. Can anybody tell me what that is without drawing any structures?
Non-polar.
How do we know that's nonpolar? Two nitrogen. What's the difference electronegativity between nitrogen and nitrogen? 0, right? So this is nonpolar, but again, if you didn't catch that, just draw it. But this one, if we draw, it does have a lone pair around the central atom. That exception I told you about. But doesn't have any difference, so it's nonpolar. Therefore, what type of intermolecular force?
London?
London dispersion. Yeah. We good? What about NaCl? What type of compound is that? Ionic compound, a metal and a nonmetal. So what's the intermolecular force do we have? Ion, ion. We good? And the last one, CH2Cl2. Ionic or covalent? If you can't tell me just by looking at it if it's ionic or covalent, what does that tell me you need to do? Study the different types of classes on our periodic table. Study the elements, get them down so you know where they are. And if you don't, just have your periodic table handy. At least know where the line is between the metals and nonmetals, right? This is covalent, good. No metals in it. No polyatomic ions. So this is a covalent compound, so we got to determine if it's polar or not. What does it look like just by looking at it? Oh, I can't tell. That's okay. You don't have to. Why does it look polar? Because it's not symmetrical. But again, if that doesn't click to you, then just draw it. Four regions, this is tetrahedral, so it's going to be something like this. Whoops. I was just drawing the same thing, sorry. Does it matter where we put them, guys? It doesn't. They all have an angle of 109 degrees, so try to make it easier for you. Okay? So this part right here, is that polar or nonpolar? If you don't know, then you have to just check. Hydrogen is 2.1, carbon is 2.5. Is that polar or nonpolar? Nonpolar. So we don't have to worry about those because those are both nonpolar. Carbon, chlorine, polar or nonpolar? That's 3.0 and 2.5. That's barely polar. Which one's partial negative? The highest one, which is chlorine, partial negative, partial negative, partial positive. We can draw a line that separates the positives from the negatives. Makes this polar. Is it hydrogen bonding? No, because hydrogen is not bonded to oxygen, nitrogen, or fluorine. The top three on the periodic table, top three highest electronegative elements. So that makes this what? Dipole, dipole.
So
Yes.
for it to be like hydrogen bonding, if there's like one hydrogen bonded to like nitrogen or the oxygen or the chlorine, like for
Yep.
example, like in the HOCl, would that one be a hydrogen bonding?
Let's see. HOCl. So the way that it's written here shows that it's like this. And the oxygen is bonded to the hydrogen, so it is hydrogen bonding.
So as long as there's like one bond, then it would be a hydrogen bonding.
Okay.
Because it's just the one.
So it doesn't matter how many there are, but when we say hydrogen bonding, are we talking about this guy right there? We are not. We are talking about the weaker attraction between another one. Right? This is the hydrogen bonding. Are we good?
Yeah, that
But how do we tell it has hydrogen bonding is because of this. Good? Any other questions? There's more on the practice sheet. Now, there is a little bit more about the melting point, boiling point. We didn't do it in my last class, but here's the thing. If you guys, because we ran out of time. We still have about 30 minutes in here. We can stop now and match what they're doing, or we can get as far as we can so we can have more review. It's up to you.
Let's keep going.
Okay, good. Any questions on how to determine what type of intermolecular force we have? Okay, let's move on to phase changes. Melting point, boiling point. So just like up here in this table, if it has a stronger intermolecular force, it has a higher melting point, boiling point. So step one, do you like all these steps, or is that confusing, or do you like it?
Steps are good.
Okay. So determine if a compound is polar or nonpolar. That way we can determine if it's what type of intermolecular force we have, right? In fact, we could just say determine intermolecular force. And we can follow these steps to do that, right? Step two, we put them in order. London dispersion is lowest in melting point, boiling point. Then dipole-dipole. Then hydrogen bonding. And then ion-ion. Does that make sense? What happens if they're the same type of intermolecular force? Then we move to step three. If they have the same intermolecular force, then we check the molar mass. Now, we haven't learned molar mass yet. Is there any masses on the periodic table? Yeah, what do we call this? Atomic mass. Do you know where the atomic mass is on the periodic table? That's the bottom number. Okay. So, the higher the let me say this. More molar mass or more atomic mass goes to higher melting or boiling point. Now I'm going to give you an analogy. It's not the exact same thing. But you have a pan of water on the boil that's just 1 cup. Another pan of water on the boil that's 1 gallon. Which one takes more energy to boil? The gallon takes longer. Takes more heat, right? Now that's not exactly this. So if we have more, it's going to have a higher melting point, boiling point, kind of ish. Okay, it's not the exact same thing, but maybe you can kind of think about it that way. The bigger it is, then it takes longer to boil. Higher melting point, boiling point. So let's do an example. And this will be on the exam. So we want to put in order by increasing melting point. So if we have H2O, NaCl, O2, and HCl. Which one's the lowest? Which one's the highest? In order, from lowest to highest. What kind of intermolecular force do we have here? Hydrogen bonding. We just did this so we know. If you don't know, follow the steps. Good? What about NaCl? Ion-ion. It's an ionic compound. What about O2? It's nonpolar, so it's London dispersion. Good. And HCl? Maybe we don't know that. We didn't do that one today. Looks like that. 2.1, 3.0, partial negative, partial positive. It's polar. Is it hydrogen bonding or dipole-dipole? Dipole-dipole because the hydrogen is not bonded to an oxygen, nitrogen, and fluorine. Good? Okay, so which one's the lowest melting point? O2, right? Then what's the next lowest? HCl. Then H2O, are you with me? And the highest is the ion-ion or NaCl. We good? Okay, that one wasn't too bad. Let's try one that's a little bit more complex. Do the same thing for CCl4, CBr4, or CH and CH4. Any of them ion-ion? Okay, so we got to check their polarity. What's the molecular geometry for these things? They're all tetrahedral. And they're all symmetrical. Therefore, they are all nonpolar. That means they are all London dispersion. And if you can't see it that quickly, it is okay. Go through step by step by step. Do you want to go through some of those steps? Okay, let's do it. Okay, I just drew the Lewis structure. So now we draw the molecular geometry. Looks something like this. Is the chlorine-carbon bond polar or nonpolar? You don't have to memorize it, you just have to look. It is a polar bond. So now we have to determine which is partial positive, partial negative. Chlorine is partial positive or partial negative? partial negative because it's more electronegative. Are you all following me? Does anybody have a question on this? Can we separate that one? No, that tells us what? Nonpolar. Therefore, London dispersion. Are we good? We can do the same thing here. Is this a polar bond or nonpolar bond? Bromine, which is, what's the electronegativity value? 2.8, 2.5. Is it polar or nonpolar? 0 polar bonds. Therefore, this is nonpolar. Therefore, London dispersion. This is only a carbon-hydrogen compound. Therefore, nonpolar. London dispersion. Okay, they're all London dispersion. Now what do we have to check? Molar mass. So let's calculate the molar mass. This is our first time doing this. Let me show you how to do it. It's not too bad. So we got CCl4, CBr4, and CH4. What is the molar mass or the atomic mass of carbon? 12.01. Plus, what's the molar mass or the atomic mass of chlorine? 35.45. Then we got to multiply that by how many? 4. It's kind of like what we're doing with valence electrons, right? But now we're looking at atomic mass instead. And we add those together, and what do we get? About 71, 140, 142, 144, 154. Use a calculator. Make sure I didn't make a mistake, because if I made a mistake, we all get it wrong. It's probably more like 150, huh? 151? Oh, I was right?
Yep.
Okay. What about, so do the same thing here. This is 12.01 for the carbon. Bromine is what? Is that one 80?
79.90.
Basically 80. We add those together, we get 320, 332-ish. And then this one right here, 12 plus 4, about 16. So which one has the lowest melting point? CH4, right?
Methane?
Methane. Then which one? CCl4, and the highest is CBr4. Now guys, gals, did we have to do that? They all have carbon in it. They all have 4 of the same element in it. Look at the mass of this. That's a 1, that's a 80, and that's a 35. But you can add them all up. You can. Okay? Questions on that? Okay, that is all about polarity and intermolecular force. Should we call it the night, or do you want to keep going? Keep going?
We
I
need
don't-
all of Thursday.
Okay. review all Thursday? We can. All right. Any questions on this, guys? So a lot of steps, right? So you're going to have to just kind of study this and try to make sense of it and get it in there. And that's why I'm wondering, do you want to keep going?
Yeah.
Okay, okay. All right. So now we're going to do solids. There are different types of solids. So we have ionic solids. Ionic solids have what type of intermolecular forces? Ion, right? So in comparison to the other ones, they have high or low boiling point, melting point? High. Does that make sense? Why? High melting point. And a lot of times we don't have to worry about boiling point because it's really, really, really high. Okay. But we could. High melting point, boiling point. And since it's ion-ion, that's a very strong attraction.
Would you just say strong ion?
Uh-huh. And we know that from ion-ion, right? And that's why it has a high melting point, high boiling point, right? And that's also why they're harder. These solids are harder generally out of all of the solids we're dealing with. We good with ionic solids? Well, we kind of talked about properties of ionic compounds. That's why they have the properties they have. Questions on those? Do we know how to tell if it's an ionic compound just by looking at it yet? If we don't, get our classes down. If it has a metal in it, it's an ionic compound. Metal and a nonmetal, it's an ionic compound. Or if it has a polyatomic ion in it and it's neutral, it's an ionic compound. Okay? The next type of solid we're going to talk about is molecular solids. So these ones deal with hydrogen bonding, dipole-dipole, and London dispersion. So these properties are going to be spread out quite a bit. But in comparison to ion-ion or ionic solids, weaker attraction. Lower melting point, boiling point. We're kind of just summarizing what we already talked about today, aren't we? They're softer. Okay, and we're going to have two types of molecular solids. We have crystalline solids, like sugar. These ones are going to be a little bit harder. because this is hydrogen bonding. Sugar is a polar molecule. How do we know? Because polar dissolves polar. Like dissolves like. Let's write that down. Means polar dissolves polar. Nonpolar dissolves nonpolar. So how do we know sugar is polar?
Dissolves in water.
It dissolves in water, and water is polar. I'm not going to draw the sugar molecule because it's huge, but it's got a lot of oxygen and hydrogen bonds in it. Therefore, it's hydrogen bonding. Another type of solid for molecular solids is amorphous solids. What the heck is that? So that's going to be like butter, wax. Good? Petroleum jelly, all that stuff. So those are the extremes. Well, kind of. We got two more solids to talk about. So that deals with ionic and covalent. What else is there? We have covalent network solids. These are held together not by intermolecular forces, but by covalent bonds. And a bond is always stronger than a intermolecular force. By covalent bonds. And there's just a few examples of covalent network we're going to talk about. Diamonds. What's diamonds made out of? Carbon. It's just carbon. So these carbon bonds, they're just bonded together through covalent bonds. And what's the difference between diamonds and coal? How tightly they're packed. So in diamonds, they're really tightly packed. You guys ever seen the 1980s version of Superman? Yeah, you shouldn't watch it because it'll make you dumber. But it has really cool special effects. Wait. But anyway, Superman, he takes a piece of coal and he squishes it with his hand and he turns it into a diamond for Lois Lane, right? I mean, it's okay. I mean, he could do. I mean, Superman's tough. He's right. Okay, but anyway, tightly packed makes it harder, higher. All the properties just really go up. So these properties have very, very, very high melting points or boiling points. Very, very, very hard. So it just enhances all their properties. And then the last type of solid is metallic solids. And these are held together by a sea of electrons. And this is what makes metals conductive. The electrons are able to move wherever they need to go. So, for example, we're almost there. We got 3 minutes. So if we have a chunk of metal here, our metal has fixed protons, right? And then if we have an object that is positively charged, then not all of the electrons, but the valence electrons go over to the side where the positives are. They can move, kind of like a sea of electrons. Since they can move, it allows energy to flow through that material a lot easier, making it conductive. But they also have high melting points, high boiling points. They're malleable and ductile. We talked about these properties, right? But if we put a negatively charged object by something, then the negatives go away from it, right? And again, this is just the valence electrons. The valence electrons are free to move. Any questions? So there's a question on the test that says, what kind of material am I talking about? What kind of solid am I dealing with? So you got to look at all of the things. Metallic solids have high melting point, high boiling point. What else has high melting point and high boiling point? Covalent network. What else? Ionic solids. So you can't just go with one of them. Okay? If it's non-conductive but it has very high melting point, what are you going to call it?
The covalent network? It's not conduct.
But there's probably some other ones too. So it could be that one. It could also be ionic solid, right? Ionic solids are also non-conductive unless you dissolve them, right? And what if, I can't remember all the things it asks from the top of my head, but, so you got to look at everything. Good? Okay, it's 8:50. We made it. Is that worth it?
Yes.
Okay, come with questions, ladies and gents. If you need a study guide, come grab one.